Hi, in this video we present our paper, Using Deep Convolutional Neural Networks to Detect Render Glitches in Video Games, for the AIIDE 2020 conference. We will present with the following outline. First, some background regarding the problem tackled. Then, we will present the approach followed, the data used, and the experimental setup. After, we will present the main results, and follow with a discussion on some implemented modifications. We will finish commenting on some future work. First, we present the objective of this paper, which is to automate the glitch detection process in video games. Right now, this process is completely manual, which translates in testers playing the game and coming across different graphical errors. The glitch detection problem is defined by the following. First, glitches are uncommon events, particularly in later stages of video game development, which makes spotting them a slow and labor-intensive process. On the other hand, the glitches are actionable, meaning that they can be fixed, making finding them highly valuable when trying to develop high-quality games. And lastly, most of them are well-defined, this meaning that most of them are of the same kind, with well-known mechanisms, which allows us to generate samples in order to train a model to detect them. The scarcity of the glitches allows us to frame the problem into anomaly detection, where we can differentiate three approaches: unsupervised, semi-supervised, and the one we used, supervised. This is not a common approach in general when using anomaly detection, mainly due to the scarce and unexpected nature of the anomalous instances. But when working with video game images, most of the glitches belong to the same type, and we can generate our own examples, which means we can get a balanced dataset for training our model. In this study, we primarily focus on texture glitches, framing this as a classification problem, using 800 by 800 images as input to a deep convolutional neural network, with 5 classes output, 1 for normal instances and 4 for 4 different kinds of glitches. We used deep convolutional neural networks architectures like ShuffleNet, ResNet, MobileNet, or VGG, obtaining the most promising results with ShuffleNet. We focused on texture glitches, generating 4 classes that can be grouped in corrupted and missing textures. Here we have an example for the corrupted textures. Being the normal image in the left, we see a stretch texture in the central image, which in practice occurs when the object is somehow deformed. In our case, we generated this glitch by scaling the texture in one particular direction. On the right, we see a low-resolution texture glitch, caused by a low level of detail, generated in our case by scaling uniformly the texture and resulting in a blurry texture. Now, we present examples for missing textures. On the center, we can see a missing texture, which happens when the object itself crashes, which means that no textures are rendered in the object whatsoever. In contrast, the placeholder texture glitch occurs when the texture is not available, rendering a default texture in the image. In this case, we have used a white texture. To train the model, we use data from 3 different video game environments in Unity to assess the versatility of our approach among different kinds of data. The first one was created using the assets from the Book of the Dead in the Unity Asset Store and tries to resemble a realistic video game. The second has a more stylized feel, using assets from the FPS Sample environment in Unity. And the last one uses objects like skulls and swords, taken from the Viking village set in the Unity store. To train the models, the setup is as follows. First, we collect the data, taking captures in the adequate resolution in Unity. The data is generated so it's balanced, having the same amount of samples for every class. This means 20% for every class. Then we split the data using 80% of the data for training and 20% of the data for testing. Then the deep convolutional neural network trains for 100 epochs. For every epoch, the model is evaluated, and the metrics are computed averaging the performance of the last 20 epochs. The main ones computed are accuracy and the confusion matrix. The first one allowing us to compare different performance regarding hyperparameters like the batch size or the learning rate. And the confusion matrix allowing us for a more in-depth understanding of the performance of the network. After training the model, we display in this slide the best performing model. On the right, the confusion matrix shows the classes for which the model performs best, these being missing textures, both missing and placeholder. On the other hand, we can see some confusion with corrupted textures. This agrees with the fact that these are also difficult for humans to recognize. Overall, the performance is coherent among the different datasets with similar confusion matrices. If we look at the general accuracy, this is similar for the three datasets we mentioned. When developing video games, a striking placeholder texture is used to make it easier for human testers to locate these glitches. In the same fashion, we tried using a pattern placeholder texture, and as a result, we improved the classification of placeholder textures. If you take a look at these confusion matrices, on the left, we see the performance when a white placeholder is used, and on the right, when a placeholder with a pattern is used. If we focus on the placeholder column, we see that the misclassification is much bigger when using white textures. This is because in these samples, elements with white parts were misclassified as glitches, which does not happen when we have a characteristic texture. The results we showed are only one part of the exploration we have done around this problem. In order to assess how the performance of our method was influenced, we tried several modifications. One easy thing that we tried was to use a broader classification by grouping the glitch classes with corrupted textures and missing textures. When comparing both the broad grouping and the original class structure, no significant improvement is observed. In this slide, we can see how the confusion matrices in different group settings. Going one step further and aiming to provide some localization information for the glitches, we tried semantic segmentation, which essentially provides pixel-wise classification. With this approach, we obtained good defined heat maps with sharp edges, particularly in missing textures, although this approach failed to locate corrupted texture glitches. In that sense, this failure was partly due to difficulties we had defining the target for training the semantic segmentation approach. But on the other side, this approach was very slow, both to train and execute, and we were not using the best of it, since the use case was not the most appropriate, having all the glitches centered in the image. Semantic segmentation, on the other hand, could really come in handy when testing video games in other settings, like using a flying camera to analyze the scene. Another thing we tried was aggregating images for classifying objects as glitchy or normal. In this environment, we have the advantage of having complete control of the scene by changing the camera and factors like the illumination conditions. In that sense, we can feed the model not one, but several images from the same object and combine this information to improve the classification. What we did was simply feed different number of images to the same network and average the classification probabilities. Doing this, we managed to slightly increase the accuracy of the method by 1.5% using simply 2 images, but clearly reaching some point of saturation when the number of images was increased too much. To better understand the behavior of the model, we used a measure of confidence by modifying the classifier to a Gauss network. Using this, we confirm our intuition. On the confusion matrices, looking at the mean probability and the mean confidence of the model in every cell, we can confirm that the model classifies more easily missing textures but struggles with the corrupted.
Our results encourage for further exploration, and we still have many remaining challenges. The first one is naturally how to cover essential parts of the space. Here we can use reinforcement learning-based approaches to ensure that we effectively visit all critical parts of the map. We can also connect the reward signal to the number of graphical glitches it finds. Our current model don't use location information. Being able to extract location could probably greatly improve the performance of the test. We might also use sequences of frames to find flickering and other animation glitches. Last, we also explore how to find other classes of glitches using unsupervised and semi-supervised anomaly detection approaches. This concludes our presentation. Thanks for listening.